Welcome! Today we're going on an adventure with a special vehicle as it tackles a series of bridges and the problems they bring. We'll figure out each problem, find a smart solution, and see how the laws of physics can help us. Let's go! Our vehicle hits its first roadblock, a narrow bridge. It's strong but not wide enough for our vehicle, so it can't move forward. What can we do? We can make the vehicle thinner by changing its design. This shows how important shapes and adaptability are in overcoming physical limits. With a slimmer shape, our vehicle can now cross the bridge. The idea we used, design geometry. Design geometry means changing an object's size to fit into spaces. By making the vehicle narrower, we solved the width problem, letting it go through tight spots without losing its ability to work. This idea is used a lot in transportation, like designing vehicles that can fit through tunnels or narrow roads. Before we move on, don't forget to like the video, subscribe to the channel and share this video with your friends. Thank you. Our second obstacle is even tougher. Even thinner, the vehicle's wheels are too far apart to fit on the bridge. The answer needs a bigger change. We'll swap the outer wheels with a bigger pair right in the middle of the vehicle. This puts the weight on the center, making it more stable on narrow surfaces. This design uses the idea of static equilibrium, where the support force has to be right below the center of gravity to stop it from tipping over. The idea we used, static equilibrium. In static equilibrium, all the forces and turning effects on an object add up to zero. Moving the wheels to the center lines up the center of gravity with the support point, making it less likely to tip over. This idea is super important when designing things like suspension bridges or off-road vehicles. As the bridge gets even narrower, a new problem pops up: uneven weight. With the engine on one side, the vehicle's center of gravity shifts, making it lose balance and fall over. The solution is easy but works well. We'll move the engine to the middle of the vehicle, making sure the center of gravity is in line with the wheels. This change makes sure the vehicle stays balanced even on super narrow bridges. The idea we used, center of gravity. The center of gravity is the point where an object's weight is concentrated. If the center of gravity isn't lined up with the support, the object becomes unbalanced and might tip over. By centering the engine, we make the weight even, keeping the vehicle stable. This idea is used in big machines like mobile cranes or construction vehicles. Our next challenge is getting the vehicle across a much narrower bridge. Now, even with good weight distribution, the surface is too narrow to give enough support on the sides. To fix this, we'll add support wheels on both sides that go down and touch wider surfaces below the bridge. This makes it more stable by increasing contact points. Here we're using the concept of moment, as these wheels reduce tipping by spreading forces across multiple support points. The idea we used, moment and weight distribution. Moment depends on the distance between the line of action of a force and the pivot point. Adding side wheels creates a counterbalance and spreads the vehicle's weight to more stable points. This idea is used in things like stabilizers on boats and airplanes, which help them stay balanced against external forces. The next obstacle is even harder, a bridge so thin that there's no space for extra support wheels. Without an external contact point, the vehicle needs a totally different solution. We'll add a suspension system on both sides of the vehicle. These supports push weight downwards, reducing swaying and making it more stable. The main idea here is dynamic equilibrium, where external forces acting on the system are balanced by a more even distribution of weight. The idea we used, dynamic equilibrium. In dynamic equilibrium, external forces are balanced by a structure that spreads weight evenly. The suspension system stabilizes the vehicle by counteracting side-to-side swaying and distributing forces downwards. This idea is really important in architectural design like cable cars or gondola lift systems. Our final challenge is getting the vehicle across a tightrope, a super narrow and flexible surface. Now, the suspension system isn't enough because the tightrope allows for movements that mess with the vehicle's stability. To fix this, we'll change the vehicle's wheels adding guides that let the tightrope pass right through them. This makes sure the vehicle stays aligned with the tightrope, reducing swaying and ensuring linear motion. This design uses the ideas of controlled friction and uniform tension, where the tightrope acts as a stable track. The idea we used: controlled friction and uniform tension. Controlled friction makes sure the wheels stay in contact with the tightrope, preventing slippage. The uniform tension of the tightrope acts as a rigid track, making the vehicle more stable. This concept is used in railway systems or zip lines, where movement needs to stay consistent on taut surfaces. Now it's your turn. What did you think of these solutions? Can you think of other ways to overcome these challenges? Share your thoughts in the comments below. And don't forget to like, subscribe and share this video with your friends. See you next time.